Hello and welcome to another Let's Study video on programming principles and practice using C++, 3rd edition. Today we will be going through Chapter 3's review and terms. So here I have written a LibreOffice document on providing both the review questions as well as my initial first revision responses to these questions. And so I'll just read through these here. So we have question number 1. What is a computation? And I like the concise response of the production of some output based on some input. And then we have question 2. What do we mean by inputs and outputs to a computation? Give examples. So I put inputs with the examples of keyboard strokes, numbers, text, and files, and outputs examples is being screen displays, numbers, text, and files as well. And then we have question 3. What are the 3 requirements a programmer should keep in mind when expressing computations? And first of all, computations must be correct. Second of all, they must be as simple as can be without going much further, so that they can be edited and modified for the future. And third of all, to be efficient, or to use the least amount of resources and dependencies as possible. We have question 4. What does an expression do? An expression evaluates to some value by computing with operands and operators. We have question 5. What is the difference between a statement and an expression as described in this chapter? I responded with, a statement is an action and an expression is an evaluation. I'm going to edit my response to say an expression is an evaluation to a value. Number 6. Now this one's really confusing. It always is for myself. What is an L value? List the operators that require an L value. Why do these operators and not others require an L value? And so I think that this response is at least beginning to become adequate. So an L value is a reference to an object that can be assigned a new value. Notable exceptions is we have the constant expression objects, which they're assigned at compile time, and they can, I believe, not be used. They can be used as an L value, but you will produce some error if you use a constant expression in an L value format. But you won't get an L value compile error. You will get you tried to change a const expression error. And then we have const, which is assigned during runtime, so it can be used as an L value once. And then if you tried to change it again or use it as an L value again, it would fail with a different error, such as trying to modify a const value. So I have these examples here with int x equals 10 in which case x here is an L value. Now you get the name L value because it is on the left side of an assignment operator, although there are other operators which take L values or use L values. And so if you think about it here, we have the number 10, the literal value 10. And if we try to assign the literal value 10 the value of 2, it makes no sense to do something like that. 10 is not a L value, it's not a modifiable value, it is a value known at compile time. It is a constant expression or a literal value. It is a literal value. So then I think I have a list here which hopefully is accurate of L value requiring operators. So operators requiring L values. Let me change that wording up. So then we have the assignment operator is the biggest one. It very much takes an L value. Requires an L value on the left-hand side. We have the pre-increment and the pre-decrement. Actually, well, if we just have if we have an increment or decrement operator, such with plus plus or minus minus, which doesn't show a gap in LibreOffice in this font. It requires an L value to be modified. So the increment operator is trying to increment up that value by 1, and if it cannot change that value, you're going to have a problem. And then we have the compound assignment, which has it has an assignment operator with it, and so in which case, just like before, it's trying to change a value, and that value must be an L value. And I put these in, but I'm starting to question them. But we have the output operator and the get from operator. I'm really starting to question them to the point that I'm gonna take them out. And an R value is simply not an L value. If it's either an L value or an R value, there's nothing really else, I believe. So question 7. What is a constant expression? My response: an expression which is computed once during compilation and is unchangeable during runtime. Then we have question 8. What is a literal? And I defined it as a C++ language-defined expression which evaluates to a value, such as the characters 100 being the literal value of integer 100. We have A in single quotes, which is representative of the value. I forgot what the value, ASCII value of A is, but it is the literal value of the car or the character A. Or we have 1.3, which is the literal representation of a double floating point number of 1.3. Oh, looks like we have an unanswered question here. What is a symbolic constant and why do we use it? Okay, give me a second. So I had to look a little farther into the book, into chapter 6, section 6, subsection 1 on symbolic constants. The question was, what is a symbolic constant and why do we use them? And my quick response is, it is a named constant value, so a value that will not change, and we have given it a name. And why do we use them? We use them to provide context to their purpose. Yep. And then we have question 10, which is very much related to question 9. What is a magic constant? And give examples. I believe it's best described as either a literal value used without a comment explaining its purpose, or an ambiguously named constant. So we have the example 3.14, which you might think is pi, or some very large integer, and then we have a ambiguously named constant AB323, E342, which might stand for an error 342 number or value. And then we have an example from earlier in the book. We have age equals -1, which we used -1 as a placeholder for an age that has yet to be defined. In which case, we could have defined it with a symbolic constant, such as giving it the name unknown age. So we can have a const expression int unknown age equals -1, and then have that age equals unknown age at the beginning of the program, instead of having a magic constant -1, because what does -1 mean? And it's especially confusing if we did not write a comment explaining what -1 is being used in this context. Then we have question 11. What are some operators we can use for integers and floating point values? And so we have the assignment operator. We have the assignment operator, addition, subtraction, multiplication, division. So these are our math operators. And then we have compound assignment here. So we have an addition assignment, a subtraction assignment, a multiplication assignment, and a division assignment. And then we have our conditional statements, or conditional checks, which is equals to, not equal, less than equal to, greater than, and finally greater than equal to. Then we have question 12. What operators can be used on integers but not on floating point numbers? So there's only one operator that can be done, I think, or there's only one that we've been shown so far, which is the modulo operator, or modulus, which is used with the percent sign, and provides the remainder after being divided by the right-hand operand to the left-hand operand. You could find it, as well as the modulo assignment operator. You could find information on page 34 and 35. And bonus information here, I added this myself. A switch can be used with integers, but not floating point values. A switch statement. So then we have question 13. What are some operators that can be used for strings? And I provided this table, which is pretty much a copy from the book, from pages 34 and 35, which we have the assignment operator, of course. We have the addition operator, which is for the string is a concatenation, which puts two strings together. The end of the first one is then continued by the first character of the second string, and it's functionally equivalent, I believe, to this append function. Then we have the read and write with the double angle brackets being shown here with the output operator and get from operator. And then we have our conditional operators, equals to, not equal, greater than equal to, less than equal to. And I believe this is lexicographical ordering. So if the left operand is, so this would evaluate the true, because A is less than B. It comes before, A becomes before B alphabetically. But also lexicographically, because it also cares about size. So, I think the example is that ape comes before apple because ape is a shorter word. I don't know. I don't particularly know the rules of lexicographical ordering. So then question 14. When would a programmer prefer a switch statement to an if statement? So we have, I have 3 examples of when I would prefer to use a switch statement. And so I think a switch statement comes right into play when we have many choices and selections based on one value in place of many if statements. And so when we're taking in an input, such as a character pressed on the keyboard, and we need to map it to possibly dozens of different values for that keystroke, and we want to do something different for each one, a switch is perfect because we take it in once at the top of the switch. We take in that value, and then we have our case and break structures below to handle all of the changes. Well, not all the changes, but all of the expected output and actions of the switch state on that input, I should say. So we can organize our computation very succinctly. And then the second situation you might end up finding yourself in is if you have identical output or behavior that you might want for several values. So what I mean is if you got some integer input, and if the value is evaluated to be equal to 3 and also 5, instead of writing a bunch of nested if-else statements, which some of them, such as if it evaluates to 3 or 5, if we're provided 3 or 5, to do the same thing in a switch statement, you can have those cases right next to each other, and then effectively very much so, they go to the exact same place, and going to the same place and executing the same function makes a lot of sense in that case. And then the third situation we might find ourselves in, which is pretty rare, is we might want the switch fall through behavior scene, which would be very difficult to recreate with if statements. Then we have question 15. What are some common problems with switch statements? And so a common problem is trying to use a switch on a non-integer character or numeration typed value. So trying to switch on a string or a float or a double. I've done that many a time. I'm expecting it to work and it doesn't. I feel like it should, but it doesn't work for reasons we don't fully comprehend yet. And then the second most common problem, I think, is forgetting to break out of a case where fall-through behavior is unwanted. So if we have a switch statement with a bunch of different cases and no breaks, or forgot no breaks, we might end up executing code we did not want to execute. So we could have some logic to execute some code based on if the number is even, and then if the number is odd. And if we forgot to add a break at the end of our case of it's even, it would fall through and perform the action as if it was odd as well. And vice versa, except if odd behavior was after the even wouldn't be executed, but the odd would be. Okay. And then finally, a common problem I have with switch statements, or potentially could, I really don't think I've ever forgotten this, is forgetting to define a default case. It's not required, but it is useful, such as providing cases for every valid input and then leaving default to handle whatever it gets as an invalid statement, and to print that out for testing purposes as well as just good error handling. We'll see more about that in chapter 4 on errors, which will be the next chapter which will be covered. And then we have question 16. What is the function of each part of the header line in a for loop, and what sequence are they executed? So I guess I misread that. So of the header line, I added part 4, the body, but I'll include it anyways. So we have for part 1, semicolon, part 2, semicolon, part 3, semicolon. Now, part 1 is designed for to be initialization. It's done first and only once before executing part 2, which part 2 is a conditional expression. So of some operands and operations, it is done at the start of every loop. Done at the start of every loop, evaluates to some Boolean value. It exits the loop if this conditional expression ever results in false. And then finally we have part 3, which is the iterator part, which is done at the end of every loop. And then I had this included, which is part 4, which is the body of the for loop, which is done with every loop after part 2 and before part 3. We can exit the loop early using the break within the body, part 4. We can exit the loop early using the keyword break, BREAK, followed by a semicolon. And if we want to return to the top of the loop after, as well as going through the part 3 iterator, if we want to skip the rest of the body of part 4 and go straight to part 3, the iterator, we can use the keyword continue. And we have question 17, which, when should the for loop be used and when should the while loop be used? I think a for loop should be used over a while loop when the loop initialization, condition, and increment operation are easily defined. Otherwise, it might be useful to use a while loop. I'll mix up this conditional expression. Iterator, incrementer. I guess part 3 would be best described as an incrementer. No, that's a word. It has to be a word. Well, I added it to my dictionary, so it is a word now. Okay. So a for loop should be used over a while loop when the loop initialization, conditional expression, and increment expression are easily defined. Otherwise, it might be useful to use a while loop. So we use a for loop over a while loop when it's convenient and quick and easy to... If it's quick and easy to define a for loop for the given looping behavior we want, it's most likely best to use a for loop over a while loop, I believe. And so we have question 18. Describe what the line char foo int x in parentheses means in a function definition. So I believe it's the line means there is a function. It is named foo, which takes in an integer argument and outputs a character. Question 19. When should you define a separate function for part of a program? List reasons. And so we have abstraction, which is to abstract away unnecessary complexity. We have division and conquering, divide and conquer, to break up a large computation into smaller units or smaller computations. And I like this one, which wasn't specified, but code reuse. If we define a function which stands on its own, it is a lot easier to take that function and use it in another program elsewhere. But also, if we're performing the same computation several times in a program, instead of having multiple places where we might want the same behavior to now be changed, we can have it referenced as a function defined in some place where we can take only one change or edit to then produce different operations or different behavior in many places in the program, which, now that I'm thinking about it, could also be a detriment. So then we have question 20. What can you do to an int that you cannot do to a string? So for an int, you can subtract two ints, you can multiply them, you can divide them, you have the modulo operator, and you can increment and decrement integers. As well as you can switch on an integer value, and I'm possibly wrong about this, but it appears true so far, but you can't const expression a string, or a string as it is. So there is no const expression string name equals some literal value, some literal string. As far as I know, I've only ran into problems getting that done. I believe you can do it as an array, but not a vector. Well, not a vector, but not as a string. But you can do it as a character array, I believe. So we have question 21. What can you do to a string that you cannot do to an int? And so for a string, you can call a specific character within that string based on location, starting from 0 to the length of the string minus 1. Each character is represented or can be referenced with an integer value of where its location is in the string. So we have string n in brackets, or we have string dot at member function, and we provide it a number, which is the index by location. Okay, this is where we bring in the word index. And so we can call a specific character of a string by location or index, unlike being unable to call a specific digit in an integer. And then we can iterate over the characters over a string. So we can go from 0 to the end of the string and perform some action on every character over that string, which, if we wanted that functionality in an int, we would have to program that ourselves. We can sort the characters of a string, which, well, sorting the digits of an integer makes no sense to me. But you can do it with a string, and you cannot do it with an int, so it goes on the list. And so effectively, we can't recall a specific part of an integer or iterate over an integer inherently, as opposed to being able to do those things with strings. I think that's what I found. We have question 22, which is what is the index or location of the third element of a vector? And so since we started at 0 and then we moved 3 places, 2 places to get to the third value, we end up at 2. 2 is the index of the third element. So whatever element you want, subtract 1 by it, and you'll get your index. So it's a 0-indexed structure. And so we have question 23. How do you write a for loop that prints every element of a vector? And easy peasy, we have a for statement with a body which prints out the vector at an index of I, which we initialize as 0, and we check to make sure that our index has not exceeded the length of the vector we're iterating over. And then, of course, in our iterator part, we want to increment up. Our incrementer part, we want to increment up I, such that we go farther along the vector. And so we have question 24, what does the vector char of type char alphabet 26 do? And this simply creates a vector of characters, 26 characters long, and that statement, after that statement, all of the characters in alphabet in alphabet vector are initialized as the null character, the 0 character. And we have the final questions, starting with question 25. Describe what pushback does to a vector. And so pushback is a member function of vector, which takes in a new value and increases the vector length by 1 and adds this new value to the end of the vector. Then we have question 26. What does vector's member size do? Which simply returns the number of elements in the vector. And added a little bonus information that it is in the size t type, which is a very big integer, I believe an unsigned integer. And then we haven't gotten into signed or unsigned data types yet. So we have question 27, what makes a vector so powerful or useful? And so I think it's most popular, what makes a vector so popular and useful? I think it's most popular and useful because it can hold many types of objects, including other vectors, and it can be easily resized. And then we finally have the last question, question 28. How do you sort the elements of a vector? And you can easily do it with the ranges object of the standard library using its sort function. Or you can do it the hard way, which is by performing a sort algorithm which uses Comparisons and swaps. There is, as described in this book already, there is apparently books and books on sorting algorithms, written on sorting algorithms. Sorting algorithms are very useful. Sorting information is a useful function or computation to be done. Yep. So that ends the review section of chapter 3. And now I have written another document, so you get a two-fer video, both the review and the terms, all in one. So then we have chapter 3's terms section, in which case we just have the terms and definitions in my definitions, or my revision 0 definitions. So then we have the terms on the left and my definitions on the right. Please don't quote me as a source of perfect information. Leave it up to I would say leave it up to the book, but I would actually leave it up to other sources than this Programming Principles and Practice book. You might want to read and look into the C++ language book, also written by Bjorn Stroustrup, as well as the cppreference.com, as well as other online resources, and ultimately your compiler for the definitions of the words it's using. I find the definitions of words and the usage of words, the creation of words, invariably useful, but also hit and miss, and it can be as confusing as well as it can be useful. It really depends on context and the task at hand. Yep, in the environment you're working in. So let's just quickly go through these definitions I've came up with for these terms. So we start with the term for abstraction, and I also sorted these after I put them in this table. Let me scooch this over. I scooch it over a little bit more. Will it fit on one page? I don't think I'm going to be that lucky. Yeah, not that lucky. That looks like good spacing. So we have the term abstraction, which I believe is best defined as the act of hiding complexity through the addition of a term, object, a thing that references that which is more complex. So I had it stuck in my head thinking about the abstract terms such as mammal. I hate to bring up biology because that's probably one of my weakest areas, but the word flower is an abstraction of a group of organisms that grow flowers, or flowering plants, and it has a very specific scientific name, which in itself is an abstraction of the group of flowering plants. So we have, say I have all the objects on my desk. Instead of listing them as they are, I can just say desk objects. Say we have a vector of strings, and each string describes an object on my desk. Now, instead of having 100 strings for 100 things I have on my desk, I have now a vector called desk things, or things on desk, which contain a string describing what it is. And so now we have abstracted the complexity of each individual item into one thing. We grouped it together. But grouping isn't the only thing that abstraction can do. And then we have the term computation, which we've already had this described earlier, but it's the production of some output based on some input. I think it's a short and sweet definition for computation. We then have the conditional statement, which I believe is best defined as a statement which evaluates to a Boolean value. So a conditional statement can be 1 is less than 2, 10 greater than 10. Yep. I think you can come up with a couple of examples on your own as well. And I shouldn't have even wasted time providing such examples. We have declaration, which I believe I define as the assignment of memory for an object. And that object can be a variable, or it can be a function, or a class. Later on, we're going to learn about that. But it's an object. And a declaration is simply, I'd like an X. And that X can be almost anything. But in the declaration, we don't have to define it yet. We could define it later or elsewhere. And, well, speaking of definition, that's our next term, definition, which I define as the assignment of values or statements, or statement block, to a data type or a function. I think I can reword that. I think the assignment of values, statement blocks, or the statement of values, the assignment of values, or functionality to an previously declared value object. I think that's better than what I had. To a previously declared object. Then we have the term divide and conquer, which is a problem-solving technique which separates a large computation into smaller ones, which can be easier to solve or compute. And then we have the else term, which is, I believe, a statement block, which only executes if a preceding if statement's conditional expression evaluated to false. And it requires a preceding if statement. And then we have the term expression, which is a group of operands and operators, optional, which evaluate to some value. We have the for statement, which is a convenient iteration structure, which involves an initialization part, which is executed first and only once, a conditional part, which is evaluated at the start of every loop, a body, which is executed every time the conditional part is evaluated to be true, and finally an iterative part, which is executed at the end of every loop. So I need to add the information that it exits the loop if false. Okay, I think that makes sense. And then we have the term function, which is a computation object, which takes in some inputs or none, performs some actions or none, you don't actually have to have it do anything, and returns some value or doesn't. A function is an object that refers to some block of statements or actions to be taken, and usually based on some inputs, and it usually returns some value or produces some side effect based on the actions that it took in its body. And then we have the if statement, which is a conditional statement and body, which if the conditional statement evaluates to true, the body executes, else execution begins at the end of the body of the if statement, which I just excluded from my definition. Because that's a basic thing that happens in C++. After a statement is complete, it moves down, falls through to the next, to the next, to the next statement, top to bottom. And so then we have the increment term, which I believe it increases a value by a set value. This being numerical, so either an integer, char, enumeration, or floating point value, both float and double. And it increments up by 1 using the plus, either in prefix or prefix or postfix operators of the increment. So the pre-incrementer and the post-incrementer, or by n, with n being some integer. Or actually, now that I think about it, some integer for ints and then some floating point value for some float or double. With the compound assignment operator plus equals n. Okay, and then we have the term input, which I just slapped together, is some value or thing which a computation uses to produce some outputs on. And then we have iteration, which I took straight from the book, which is doing the same thing to a series of objects. I don't really like that definition, and I'll probably change that in the future. So let's right click here and insert a comment here. I don't like this. Oh, that's all it needs to be. And then we have output, which I believe is defined as a value or an effect of a computation. And we have pushback, which is a member function of the vector class, which increases the vector's size by 1 and adds a value to the end of the vector. We have the range for statement, which is a convenient code structure which iterates over all values of a vector, array, or even a string. That simply as it is. We have repetition, which is performing an action several times. I just took that off the top of my head. We have an R value, which is editable. Is an uneditable value. Or object. We have selection, which is the act of performing some actions or not based on some input or evaluation. We have the size member function, which is a member function of the vector class, which returns the current size of the vector. I think we missed selection or just completely blanked out. Selection, which is the act of performing some actions or not based on some input or evaluation. And we also have, moving from size, we have sort, which is also which is a member function of the ranges object from the standard library, which takes a vector, string, or an array as input and sorts it with, I'm not sure if it has output, but I do know its side effect is that it does sort the vector, string, or array. And then we have a statement, which is a singular action, and it's usually ended with a semicolon. And then we have a switch statement, which is a convenient selection structure, which takes an integer, char, or a boolean. Though why? I did test that you can switch on true and switch on false, as they are. Why you would do that, I'm not sure. In a production code, it wouldn't make sense. In a testing manner, yeah, it would. I guess it makes sense now that I think about it. Not really now that I think about it again. Doesn't make sense, but I know why it makes sense. It works because the switch statement wants a numerical data type, and a boolean is a numerical data type, same as char. Okay, so a convenient selection structure which takes in an integer, char, boolean, and has a selection of different cases which are labeled with constant values, which mark the start of execution at if the input matches them. And these statements, the execution falls through these statement with these labeled locations, unless a break keyword is used to exit this switch structure. And a def case can be described. So case def, DEF, can be used to start execution if no case is matched. And finally, we have the two remaining terms. Vector, which is a list of values of a given type, which can be resized. So a vector can be a list of doubles, a list of ints, a list of strings, and unlike an array, we can make it bigger or just conveniently add on to it. With arrays, we have to be worried about the size of the array, accessing the array's range within the range of the array. With a vector, it's a lot safer and easier to work with. And finally, we have the while statement, which defined as a loop structure, which consists of a body and a conditional statement, which, if evaluates to true, the body is executed. And this can be exited with the break keyword and returned to the conditional statement with continue. So back up to the top of the while loop with continue. So that concludes the review questions and terms of Chapter 3 of Programming Principles in Practice using C++, 3rd edition. These are my personal answers, and I have a 90% satisfaction with my answers. Probably a little bit lower, but you should not be looking for me to define these terms for you. They are defined elsewhere and by more closer to the source, as I might describe it, people, as well as other source material. This is simply a studying behavior described in this book, that we come up with our own glossary, our own terms for these objects. And so as we define things in our own words, we can better learn them ourselves. So we learn what's important, what isn't, how things are connected, described in a way that makes sense to us, and matches, at least mostly, to reality. Okay, thank you for watching, and I'll be posting the next video. As well, I haven't even recorded it yet. I'll be working on the next video, which will start with the problems, the exercises of Chapter 3. And then we get to move on to Chapter 4 on errors. Thank you for watching, and have a good night.